Welcome to Factory on Air by DBR77, where smart manufacturing gets real. This is episode 20, Optimizing Intralogistics with Milk Run and Kanban. Internal logistics can make or break production flow. In this episode, we explore how two key systems, Milk Run and Kanban, help manufacturers deliver materials just in time, without excess stock or chaos. You'll hear how DBR77 uses digital twins and real-time data to model delivery routes, adjust trigger points, and test logistics scenarios before they hit the shop floor. Whether you're reducing transport loops or balancing Kanban inventory, smart intralogistics starts with simulation. Factory on Air is powered by DBR77, the platform that helps manufacturers design, simulate, and optimize every movement inside the factory. Let's get moving.
Welcome to the Deep Dive, the place where we really get into the nuts and bolts of global industry and try to make sense of it all. Today, we are heading right onto the factory floor. Not looking outwards at the big supply chains, but inwards. We're focusing on something often overlooked. Intralogistics optimization.
That internal movement, yeah.
Exactly. Now, maybe you think, okay, I don't run a factory, maybe this isn't for me. But hang on, because inefficient internal movement, just getting parts from the warehouse shelf to the line, or it's possibly one of the biggest hidden costs for businesses today.
A huge drain, often completely invisible on the balance sheet until you dig in.
Right. It's like the silent killer of profitability. We're talking real operational chaos sometimes. Delays, massive amounts of extra inventory, that expensive safety stock clogging up valuable space.
Taking up prime real estate, absolutely.
Yeah, and just this general feeling of disorder that really drags down productivity, maybe even impacts quality control. It's this deep, often ignored source of waste. So let's really unpack this.
It's so important to understand because internal logistics often falls into this blind spot, doesn't it? Companies pour money into managing raw materials coming in or shipping finished goods out.
The big, obvious flows.
Exactly. But that middle ground, getting things from step A to step B inside the walls, that's where inefficiencies can just multiply like crazy. And the disorder you mentioned, it translates directly into wasted labor, people searching for parts, extra trips with forklifts or carts, and, of course, the huge cost of carrying inventory. If a part just sits there for days before it's needed.
That's tied up capital.
Tied up capital, wasted space, increased risk of damage or obsolescence. It all adds up.
So what's the plan? How do we tackle this?
Well, our mission today really is to dive into two globally recognized systems. They're specifically designed to cut through this internal chaos and bring real precision to how materials flow inside a facility.
Okay.
We're talking about the Milk Run system and the Kanban system.
Right. I've heard those terms. They pop up a lot in manufacturing discussions.
They do. And they're not just buzzwords. They represent two, distinct but sometimes complementary approaches rooted in lean manufacturing thinking. But, just understanding the philosophy, that's only the start.
Okay, there's more to it.
Oh, much more. The critical difference now between, say, okay results and real success in modern manufacturing is how you use data and advanced digital modeling, simulation. That's how you design and actually perfect these systems for your specific environment.
So it's not just picking one off the shelf.
Not at all. We'll touch on how certain platforms, those capable of sophisticated digital modeling, like DBR77, for instance, are pretty much essential now. They help you move past guesswork, past intuition, and get to truly precision-engineered material flow, tailored exactly to your production setup.
Precision engineering for material flow. I like that. It really elevates it beyond just, moving boxes around.
It is engineering, absolutely.
Okay, so let's break them down. Milk Run and Kanban. Foundational strategies, you said, but they work in fundamentally opposite ways.
Well, they control flow differently, yeah. Let's start with the Milk Run.
All right, Milk Run. This one sounds descriptive.
It is. It's all about organized, scheduled delivery. The analogy you mentioned before is perfect. The old-fashioned milkman.
Ah, right. Delivering to multiple houses on one route.
Exactly that. Think about it. The milkman didn't just grab one bottle, drive across town, deliver it, then zoom back to the depot for the next single bottle. That would be incredibly inefficient.
Totally wasteful.
Right. They consolidated multiple deliveries onto one optimized vehicle, following a single, planned, efficient route, hitting multiple spots in sequence.
Okay, so apply that to the factory.
In the factory, the Milk Run means you have, say, one internal cart, maybe a tugger train, or even an AGV now.
An autonomous guided vehicle, right?
Yeah, and it follows one organized, scheduled route. It delivers materials to several different production points, the spots right beside the assembly line where workers need them.
Line-side inventory locations.
Exactly. And often, it might also pick up empty containers on the way back, or maybe even finish sub-assemblies going to the next stage. The key benefit is standardization. You drastically cut down on all those random, redundant trips.
So it imposes a rhythm.
A predictable, rhythmic structure. It's essentially a scheduled push system, but it's highly efficient because those routes are fixed, calculated, and optimized.
Okay, scheduled push. Got it. So the milk run dictates when and where materials go based on a timetable. But then Kanban, you said that's a pull philosophy.
Precisely. Kanban is the quintessential pull system. What that means is it's a material flow control system based entirely and only on consumption signals.
Right. Nothing moves until it's needed downstream.
Exactly. You don't move material, you don't order the next batch until the very next step in the process sends a signal saying, hey, I've actually used up the last batch you sent me.
And Kanban itself, the word, it's Japanese, right? It means sign or signal.
That's right. Signboard or billboard. It's fundamentally a signaling mechanism. That's its core function.
So what are these signals? How does it actually work on the floor?
Well, those trigger points are the operational heart of Kanban. Historically, it might have been a physical, laminated card in a pocket on the bin. Or maybe just a designated empty bin itself was the signal. When the bin was empty, that meant send more.
Simple, visual.
Very, but now, of course, in more digitized plants, those signals are often generated electronically, automatically.
Like how?
Think RFID tags on the bins, maybe sensors detecting low levels, or electronic signals sent directly from the assembly station back to the warehouse management system, WMS, when the material level hits a preset minimum threshold.
So it's faster, less prone to error.
Generally, yes. Lost cards aren't an issue, for example. But the critical function, whether it's a physical card or an electronic blip, remains exactly the same. Orders and deliveries are only triggered after consumption happens. And that's the mechanism. That's what ensures your supply closely matches the immediate real-time demand at the point of use. It lets you shrink or sometimes even totally eliminate those big safety buffer stocks right there on the line.
So milk run is the optimized delivery schedule, the how and when. Kanban is the optimized signal for what to deliver based on actual need.
They sound like they could work together.
They absolutely can, and often do. They're like strategic partners, as you said.
Okay, so if you combine these or use them strategically, what's the big picture goal? What are we aiming for?
Fundamentally, the goal is supporting the just-in-time principle, JIT.
The classic lean manufacturing concept.
The cornerstone, really.
Yeah.
JIT aims to produce only what is needed, exactly when it is needed, and only in the amount needed. No more, no less. And these two systems, milk run and Kanban, are absolutely foundational to actually achieving those JIT ideals in practice.
How so? What are the immediate wins?
They both work towards the same very tangible benefits right away. First, significantly limiting your stock and inventory levels everywhere, which frees up cash and space.
Exactly. Valuable physical space, precious working capital. And second, they dramatically increase the clarity and transparency of your processes across the whole shop floor because material movement stops being chaotic and haphazard.
Right. Driven by who shouts loudest or anticipates a shortage.
Precisely. Instead, it's driven by clear system logic. Everyone can see how it's supposed to work.
That clarity does sound priceless. But let me push back a bit here. A fixed milk run path. Okay, it sounds great for standardization, but manufacturing floors, they're dynamic, right? Things change.
Always.
What happens if, say, one production line goes down unexpectedly for maintenance? Or maybe a supplier delivery is late, causing a sudden spike in demand for a part you do have internally. Doesn't that rigid, fixed route, even if it's optimized for the average day, become a bit of a liability when things get messy, especially in places doing high-mix products or dealing with fluctuating demand?
That is absolutely the right question to ask. And it leads us perfectly into why simulation becomes so indispensable. Because you're right, if you just try to implement a rigid system milk run or even a naive Kanban setup without properly accounting for variability for the unexpected, yes, it becomes brittle. It breaks under pressure.
Right.
A fixed milk run route will fail if it can't cope with those fluctuations you mentioned. That's why you can't just, draw a route on a factory layout map with a marker pen or arbitrarily decide your Kanban trigger point is 3 bins full. It needs more rigor.
So this brings us to the tools needed to make it work in the real world.
Exactly. Which is our section 2, the essential tools of simulation and data. These are what transform the theory, the philosophy, into a robust, flexible, working reality.
Right, we're moving past the concepts now and into the actual engineering of the flow. So the big question for, say, the plant manager or the industrial engineer listening is, how do you know? How do you know if a fixed milk run route is truly better for your specific facility than maybe a more decentralized on-demand system?
Or maybe a hybrid.
Or a hybrid, yeah. Or even more complex, what is the optimal delivery frequency for those thousands of different parts you might be handling? How often should that milk run cart actually run? Every hour, every 30 minutes.
And how many carts do you need? What size should the containers be?
Exactly. The human brain just can't compute all those interacting variables simultaneously. Trying to optimize that manually feels impossible.
It essentially is, beyond very simple scenarios. And that's where sophisticated digital modeling, simulation, comes in.
Okay, so how does simulation help here? What does it actually do?
Well, think of it like creating a mathematical digital twin of your factory floor. It's a virtual model, but one that specifically focuses on your real-world material flows.
A digital replica of how things move.
Precisely. And the power of this is that it lets us plug in all those variables we just talked about, the different routes, the frequencies, the container sizes, the number of carts, even potential disruptions like machine breakdowns.
And you can just run experiments.
You run experiments, you watch how the system behaves under different conditions, different pressures, but crucially, you do it all in the virtual world without disrupting your actual ongoing expensive production operations.
Okay, that's a huge advantage. No costly real-world trial and error.
Exactly. So let's talk specifics. What do you need to model? It can't just be drawing lines on a map in the software, right? It must be deeper than that.
I assume so, yeah. It needs to capture the gritty reality.
Absolutely. The modeling has to be granular. You need to map out the exact milk run routes and paths, noting things like, speed limits in certain aisles, maybe intersections where congestion occurs.
Bottlenecks.
Bottlenecks, yeah. Then you model the required delivery frequencies for every single component based on their different consumption rates at different assembly stations.
Okay, so part A might need delivery every hour, part B only twice a shift.
Right. And you model the physical capacities. How much can each container hold? And critically, how much can the internal transport cart itself carry? What happens when that cart is full halfway through its route, but it still needs to make 2 more stops? Does it go back? Does it wait?
The practical constraints.
Practical constraints. But the real power, I think, comes when you model the dynamics, the interactions.
What do you mean by dynamics?
We use the simulation to identify potential points of failure before they happen in reality. Is it an overloaded delivery point where the staging area physically overflows if the cart arrives too early or with too much?
Okay.
Is it the queuing time? What happens when 3 different carts or forklifts arrive at the central loading dock at the same time? How long are the waits? Does that cause downstream delays?
You can see the knock-on effects.
Precisely. We model the interaction between the logistics system, the movement of parts, and the production system itself. This lets managers test really critical decisions virtually. For instance, what's the actual impact on overall throughput if we switch from human-driven tugger trains to AGVs? Will the routes be faster, more reliable? Or will they cause new types of congestion?
You can test those big investments before committing.
Exactly. And the key advantage, as you said, is testing countless variations, countless scenarios. Does a 20-minute milk run cycle save more money and reduced inventory than it costs an extra transport effort compared to a 30-minute cycle?
You run the simulation for both.
Run the sim, compare the outputs, inventory levels, transport costs, line-side stockouts, cart utilization, all without touching the real factory floor. It ensures the system you finally implement is genuinely tailored, truly optimized for your specific plant layout, your product mix, your demand variability, not just some generic textbook solution.
Okay, tailored, optimized, tested. But simulations, they're just models. They depend on the inputs, right?
Right, 100%. And that leads directly to the absolute foundation of all of this, the data.
Yes, the data.
Garbage in, garbage out. It's the universal truth of any modeling or simulation effort. If your model is built on assumptions, guesses, or just plain bad data,
the results won't be reliable.
Worse than unreliable, they'll be misleading. The simulation will just confirm your flawed assumptions, potentially leading you to make very expensive bad decisions.
Okay, so precision logistics needs precision fuel. What kind of data are we talking about here? It must be more than just, we use about 100 of part X per day.
Oh, much more granular than that. We need foundation data that is accurate, timely, and ideally real-time, or near real-time.
Such as?
This includes things like accurate production output rates from machines or lines, precise material consumption rates, not just daily totals, but at each specific station where the material is used, cycle times for individual tasks.
How long it actually takes to assemble something.
Yes. And the current dynamic load on all your internal transport routes. Are certain aisles congested at specific times a day? Is the elevator often busy? That all matters.
Wow. Okay, that's detailed.
It has to be. Because if your simulation assumes, say, a component takes 5 minutes to assemble, but right now, maybe due to a temporary tooling issue or a new operator, it's actually taking 8 minutes.
That timing will be off.
Your Kanban signals might trigger too late. Your milk run might not deliver frequently enough. You risk a line stoppage, all because the model didn't reflect reality accurately enough.
So, real-time, or close to real-time, data allows for what? Dynamic adjustments.
Critical dynamic adjustments. For example, using that live data helps you optimize the precise number of milk run trips needed this shift or today.
Right.
Not based on last month's average or a manager's gut feeling.
But based on actual consumption patterns right now.
Exactly. Maybe based on consumption over the last 24, 48, 72 hours. It lets you dynamically adjust the required inventory levels in your Kanban system. Maybe you need slightly larger buffers during peak season, smaller ones during lulls.
Adapting to reality.
Adapting. Establishing the perfect data-driven trigger points for new deliveries. And maybe most importantly, it helps pinpoint those really hidden inefficiencies. Logistical waste, like micro delays at transfer points or subtle traffic flow conflicts in aisles, things that simple manual observation on the floor would almost never catch.
This sounds like it requires some pretty serious technological integration, doesn't it?
Yeah.
It's not just about tracking where the bins are. It feels like you need to connect that physical movement data with, like, the business planning data from the ERP system and the machine-level execution data from the MES.
You have absolutely nailed the core challenge and also the modern solution. It is about integration. And this is where the concept of the digital twin becomes so powerful in practice.
Okay, the digital twin. We hear that term a lot, too.
Modern platforms, like the DBR77 system we alluded to earlier, are designed specifically to handle this exact complexity. They work by creating a comprehensive digital model, a true digital twin of the plan's entire intralogistics system.
So more than just the simulation model.
It encompasses it, but it's broader. This digital twin maps out every single physical route, every loading and unloading point, every storage location, and crucially, it tracks the component stock status where every part is, how many there are, ideally in real time.
That has to stay up to date in real time.
That's the integration piece. This digital model isn't static. It's constantly automatically updated. It pulls in real-time data feeds from sensor networks on the floor, maybe RFID readers, PLC data from machines, position sensors on AGVs.
Okay.
It also connects to your existing business systems, the Enterprise Resource Planning System, your ERP, which holds master data, inventory records, production orders.
The financials planning.
Right, and the Manufacturing Execution System, the MES, which knows about machine status, quality checks, actual production counts.
Got it. So it pulls all this together.
It pulls it all together. Systems like DBR77 are architected to ingest all this diverse data and use it to continuously update that digital twin. And then critically, they feed this live, accurate state of the factory into their discrete event simulation engines.
So the simulation runs on the current reality.
Exactly. This dynamic link means the model can test sophisticated what-if scenarios like, what happens if customer demand suddenly increases by 15% next month, against highly realistic operational data and the actual current physical layout and status of the factory?
Which makes the simulation results much more reliable.
Far more reliable. Before you ever commit a single dollar or euro or pound to changing anything physically on the floor.
It really is the ultimate try before you buy strategy, but for your entire factory operation.
Okay.
So we've covered the theory milk run versus Kanban. We've covered the essential tools, data, and simulation powered by this digital twin concept. Now let's get to the proof.
The results.
Yeah, the result. Because for anyone listening who's thinking about a major overhaul of their internal flow, theory is nice, but measurable results, backed by data and modeling. That's the only thing that really justifies the investment and effort. We need to see some real-world triumphs.
Absolutely. Let's look at some concrete examples.
Okay, first up, an electronics manufacturer. They were focused specifically on optimizing their milk run. What was their situation beforehand, and what did they achieve?
Well, before the optimization, they had pretty typical chaos, actually. Lots of unpredictable internal traffic. Managers constantly calling for hot runs, those emergency, unplanned, expedited deliveries, just to stop a line from going down because it ran out of a component.
Firefighting mode.
Constant firefighting. So they used simulation modeling. They meticulously mapped their routes, analyzed their consumption data, and used the model to design much tighter, more efficient routes and schedules. And critically, they linked those schedules directly to the actual consumption data signals.
And the outcome.
A major reduction in wasted effort. They managed to cut the number of those unnecessary, unplanned, disruptive hot runs by a full 25%.
Wow, a quarter of the emergencies just gone.
Gone. And because their optimized delivery schedule became so much more reliable and predictable, they gained the confidence to reduce the amount of buffer stock they kept right at the assembly lines. They cut those line-side inventory levels by 18%.
18% less inventory sitting there.
Think about what those numbers mean together. Eliminating 25% of internal transport trips. That's direct savings in labor, maybe fuel or energy for carts, and definitely less congestion, less traffic jams on the factory floor.
Less wear and tear on equipment, too, probably.
Probably. And that 18% inventory reduction, that means better cash flow because less money is tied up in stock. And it means significantly more efficient use of that really valuable floor space near the line, which was previously just clogged with buffer stock.
So it's a systemic win. It ripples outwards?
Absolutely. A real return on investment that goes way beyond just saving a bit on transport costs.
Okay, compelling. Let's switch sectors. An automotive factory. What was their story?
This facility, they'd already implemented Kanban, which was good, but they were kind of stuck in the past using old-school physical cards for their signals.
The traditional method.
The traditional method. And they decided, look, we need to bring this fully into the digital age, make it more robust.
So what did they do?
They implemented digital Kanban. They leveraged technologies like RFID tags on their component bins, maybe some simple optical sensors at the point of use to automatically trigger the pull signals.
Taking the human element and potential errors out of the signaling loop.
Exactly. It eliminated those classic failure points of manual systems, cards getting lost, maybe managers hoarding extra cards to build hidden stashes of inventory.
Oh, that happens.
Oh, it definitely happens. Or just delays in someone noticing an empty bin and physically taking the card back. With the digital system, it knew precisely the second an empty bin was consumed or passed a sensor, and it immediately generated the electronic replenishment order. No delay, no ambiguity.
Okay, makes sense. And the measurable outcome. What did shifting from manual cards to digital signals actually achieve for them?
The result was a radical improvement in reliability. They measured the punctuality of their component deliveries, basically. Did the parts arrive exactly when the system said they should? And they increased that punctuality by an outstanding 30%.
30% more on-time deliveries. That sounds significant.
It's huge because that 30% increase in punctuality, that's often the difference between a smooth-running, high-performing, just-in-time system and one that's constantly suffering from near misses or actual line stoppages due to parts shortages. It directly boosts production continuity. It stabilizes the whole assembly process.
Stability and predictability. Got it. Okay, one more example, and you said this one is your favorite. An FMCG company, fast-moving consumer goods.
Yes, I love this one because it really showcases the strategic power of the modeling aspect. Their challenge wasn't just optimizing the routes for their existing layout, it was the layout itself.
Ah, okay. What was the problem?
This company, they produce things that moved fast, high volume. They'd actually tried optimizing their internal transport routes multiple times over the years. But their logistics costs and the congestion on the floor remained stubbornly high. They couldn't quite crack it.
So they brought in simulation.
They brought in advanced simulation modeling, specifically looking at their milk run system. They linked the model to detailed traffic flow data and consumption patterns, and the model revealed something fundamental.
What was that?
It showed a basic flaw in the physical layout of the facility. The way the storage areas and production lines were arranged meant that some of their highest volume components required these extremely long travel distances across the entire factory hall.
Oh, wow.
Yeah, long, winding routes. And worse, these high-volume routes were constantly conflicting, crossing paths with routes for lower volume parts that happened to be staged nearby. It was creating inherent bottlenecks baked into the building and design.
So no amount of clever routing could fully fix it.
Exactly. The simulation proved it mathematically. No matter how they optimized the milk run sequence or timing, the sheer distance involved for those key parts and the resulting traffic conflicts meant the system would always be inefficient.
So what did the simulation suggest?
It revealed the absolute necessity of making a single but major strategic change. They needed to physically rearrange the location and layout of their main component supply points, move the storage for high-volume items much closer to where they were actually used.
Well, physical reorganization. That sounds like a big undertaking.
It was. But the simulation provided the hard data, the business case, to justify it. And the result of that single strategic layout change, driven entirely by the digital analysis, not by guesswork, was that their overall required internal transport distance was shortened by an incredible 40%.
40%, just from rearranging where things were stored based on the model?
40% less travel for their internal logistics fleet? That's massive. It proves that logistical waste isn't always about inefficient workers or bad schedules. Sometimes it's literally baked into the concrete, into the physical design of the factory.
And it was hidden in plain sight until the model aggregated everything.
Exactly. The simulation aggregated thousands and thousands of daily movements, the little delays, the cross-traffic, the queues, the conflicting priorities, things no human could track simultaneously. And it revealed this obvious source of waste that everyone probably suspected but couldn't quantify.
Managers might have felt the layout wasn't great.
Right. Intuitively, they probably knew certain runs were too long. But without the digital twin modeling the exact cumulative cost and time in congestion, in fuel of thousands of those movements every single day, they couldn't build the solid business case to convince senior management to invest in a major layout change. The model provided that vital quantification.
Okay, that is incredibly compelling evidence. These systems, when they're fueled by good data and validated with simulation, they clearly deliver massive returns. But we have to be realistic too, right? Implementing this stuff, changing how things have been done for years, it's never perfectly smooth sailing.
Never. No change initiative is.
We need that reality check. What are the hurdles? What are the common challenges companies run into when they try to implement milk runs, Kanbans, and the supporting tech?
Yeah, it's crucial to go in with eyes open. While the benefits are definitely real, there are significant hurdles that you absolutely must anticipate and address up front.
Like what? What's the biggest one?
Often, the first and maybe most significant hurdle is what we sometimes call the data trap.
The data trap. Okay.
And this isn't always just a complete lack of data, although that happens. More frequently, it's about poor data quality.
Unreliable data.
Exactly. Maybe consumption data is recorded manually and it's often imprecise. Or inventory counts in the system are constantly off by a few % compared to reality. If you can't fundamentally trust your measurement of how much material is actually being used or how much you truly have on hand,
then you can't set accurate signals.
You can't set an accurate pull signal for your Kanban. You can't calculate the right frequency for your milk run. The whole system breaks down if the foundational data is shaky. Garbage in, garbage out again.
Makes perfect sense. You can't engineer precision on a wobbly base.
What else? Then there's the sheer personalization complexity. Manufacturing isn't monolithic. Processes are incredibly diverse.
Right. Every factory is different.
Hugely different. Think about a company making huge volumes of just a few types of standard components. Their ideal milk run setup will look completely different from a company making highly customized, low-volume, high-mix products like, say, specialized medical devices or aerospace parts.
You can't just copy-paste a solution.
Absolutely not. A generic Kanban template or a standard milk run route plan. It'll likely fail immediately in one or both of those environments. The high diversity means solutions have to be highly personalized. The modeling, the route design, the container sizing, the signaling methods, it all needs to be uniquely engineered for that specific facility, those specific product characteristics, and the anticipated level of demand volatility. One size fits none, really.
Okay, so customization is key. What about the people side?
Ah, yes. You inevitably run into organizational resistance. This isn't just about installing new software or buying new carts. It's about changing fundamental mindsets and established ways of working.
Culture change.
Deep culture change, especially when you introduce pull systems like Kanban. You might be asking a veteran foreman, someone who has maybe worked there 30 years and has always relied on having huge piles of safety stock nearby just in case.
Right, the comfort blanket of inventory.
Exactly. And now you're asking them to switch. To trust a much smaller data-driven buffer level, to trust a digital signal appearing on a screen instead of their gut feeling, That requires overcoming potentially quite strong, overt organizational resistance to change.
Fear of the unknown, fear of line stops.
Fear of being the one responsible if the line does stop because the new system failed. You have to build a new level of trust in the data, trust in the system's transparency and reliability. I've genuinely seen cases where, a supervisor would intentionally ignore the Kanban signal and order extra parts anyway because they got burned by a shortage 10 years ago under the old system. They revert to the old, costly, better safe than sorry mentality.
That fear of shortage is powerful. Okay, data quality, personalization, resistance. Anything else? What about the tech itself?
Absolutely. You still have the integration headaches. These are very real. You have to successfully connect your new logistics control systems, whether that's milk run scheduling software, digital Kanban sensors and alerts, the simulation platform itself with all your existing systems. Often these are legacy systems.
Your ERP, your WMS, your MES.
Exactly. Your ERP needs to talk reliably to your MES. Your MES needs to feed accurate data to your simulation platform and maybe get scheduling inputs back. Your warehouse system needs to receive Kanban signals accurately and transmit dispatch confirmations. If those systems don't share data seamlessly, in near real time,
The whole thing grinds to a halt.
the real-time data flow breaks down and the entire optimization effort gets undermined. You get stuck mapping data fields between systems, trying to reconcile how different systems define stock status or consumption, ensuring the communication protocols are robust. It can be technically challenging.
Okay. Data, complexity, people, technology. Those are significant challenges. It really highlights why you need a very structured, disciplined approach to pull this off successfully. This isn't a weekend project.
Not even close. It's a serious transformation effort.
So based on the successful examples and acknowledging these challenges, what are the practical steps? If a company wants to move forward, what's the roadmap? You mentioned 6 steps earlier.
Yes, based on what works, it generally boils down to a structured 6-step process.
Okay, step 1 has to be data, right?
This step 1 is absolutely data gathering. It's the non-negotiable foundation. You have to execute a really thorough data collection campaign. Focus specifically on your material flows and actual consumption within the production process. And crucially, ensure that data isn't just voluminous, but validated, accurate, clean.
Okay, get the data house in order. Step 2.
Step 2 is mapping. Take that clean, validated data and create a detailed visual map of all your current routes, your current supply points, your current storage locations. Basically, map the battlefield as it exists today. This detailed as map becomes a key input for building that digital twin.
Visualize the current state. Got it. Step 3.
Step 3 is where the analytical power comes in, modeling. You take the data, you take the map, and you start modeling various scenarios. Test different milk run route configurations, simulate different Kanban loop sizes and trigger points. Use a robust simulation system again. Platforms capable of discrete event simulation are essential here.
This is where you explore the possibilities virtually.
Exactly. Determine the ideal route paths, the optimal container sizes for different parts, calculate the required fleet size for your internal carts or AGVs, find the mathematically best timing and frequency for deliveries, all done in the simulation environment before you buy a single new piece of equipment or change a single process on the floor.
Okay, model the options.
Yeah.
Then step 4 must be analyzing those models.
Step 4 is analysis. Once the simulation runs are complete for your different scenarios, you have to analyze the results meticulously. Dig into the output data. Look at the critical performance metrics the simulation predicts. What's the expected average delivery time? What are the overall projected logistics costs for each variant? What are the predicted inventory levels at line side?
Are the bottlenecks?
Where are the anticipated bottlenecks or points of conflict? You use this analysis to rigorously compare the simulated performance of your proposed to-be systems against your current real-world as-is performance, and also against any external requirements like delivery targets or quality standards.
Compare, contrast, quantify the benefits. Step 5.
Step 5, selection and implementation. Based on that rigorous analysis, you select the best variant, the most optimized scenario. Usually it's the one that delivers the highest predicted benefit for an acceptable level of risk or investment, and then you deploy it.
Just flip the switch.
Well, crucially, successful companies often don't do a big bang implementation across the entire factory at once. They usually start by implementing the chosen solution on maybe a single selected production line or area first.
Pilot project.
Exactly, pilot project. This lets them validate the simulation model's accuracy in a controlled, real-world setting, work out any kinks in the process, and build confidence before rolling it out more widely.
Smart. Less risk. Okay, pilot the chosen solution. And finally, step 6.
And finally, step 6. This one is continuous. And honestly, it's often overlooked or under-resourced continuous monitoring.
It's not set it and forget it.
Definitely not. Optimization isn't a one-time project. It's an ongoing process. You must continuously monitor the actual results after implementation. Track the real-world performance data, delivery times, inventory levels, transport costs, and constantly compare it against what the simulation model predicted. Closing the loop. You need to use that real-time performance feedback to continually fine-tune and optimize the system parameters. Maybe consumption patterns change. Maybe a new product is introduced. You need to keep tweaking the routes, the frequencies, the Kanban levels, feeding that data back into the system to maintain peak efficiency and adapt to the inevitable changes in the production environment.
An ongoing cycle of measure, analyze, adjust.
Yeah.
Okay, that 6-step process: gather data, map, model, analyze, implement, pilot, monitor, makes a lot of sense. Provides a clear path through the complexity.
It provides structure, yes.
Yeah.
Discipline.
Right. This has been a really insightful journey deep into the workings of the factory floor. Before we wrap things up, let's just quickly summarize those high-level payoffs again. Because the benefits of getting Intralogistics optimization right, they really do go far beyond just saving a bit of fuel or labor time, don't they?
Oh, absolutely. The benefits are systemic, they're strategic. When you achieve this level of precision in your internal material flow, the positive effects cascade right across the entire organization.
Such as?
Well, first, you see significantly faster, more reliable deliveries internally, which leads directly to the elimination of those painful bottlenecks that cause production delays and disruptions.
Smoother production flow.
Much smoother. Second, you achieve significantly lower inventory levels, not just at the line side, but often in central stores too. And that translates directly to better space management. You free up floor space, you shift from just reactively storing stuff everywhere to proactively managing the flow of materials.
Less clutter, more value-adding space.
Exactly. Third, you see less overall resource consumption. You might need fewer carts or AGVs. You certainly use less energy for transport. And critically, there's much less wasted time from workers, searching for materials, waiting for components to arrive, or making unnecessary trips.
Freeing up people for more valuable tasks.
Precisely. And perhaps the most critical benefit underpinning all of this is achieving that precise synchronization of your logistics operations with the actual real-time production consumption rate. You finally move away from just blindly following a rigid, often outdated production schedule push.
You react to reality, not just the plan.
You react intelligently to reality.
So, tying it all together, what does this improved internal flow really mean for the big picture, for the overall health of the business?
It means you directly increase production continuity. That's the key: reliability, predictability. You drastically reduce expensive downtime caused by internal component shortages. And fundamentally, you deliver much greater operational predictability and fluidity across the entire organization.
It sounds like it makes the whole system more resilient.
It does. So you see, this isn't just about moving bins around more efficiently. Optimizing intralogistics is a truly critical element in the transformation towards modern lean manufacturing, towards achieving those just-in-time principles in a sustainable way. It stabilizes your entire production system, especially when it's under pressure from changing demand or other disruptions.
It builds that competitive edge.
It really helps build that competitive edge needed in today's volatile markets.
Exactly. And that, I think, leads us perfectly into our final thought for you, the listener, to maybe chew on after this deep dive.
Okay.
If that one fast-moving consumer goods company we talked about, if their digital modeling efforts revealed they needed to physically change their factory layout, and doing so shorten their internal transport distances by a staggering 40%, it makes you wonder, doesn't it? What other potentially obvious sources of logistical waste might be hidden right now in your current operations, simply because they haven't been properly mapped, measured, and modeled digitally?
Good question.
And maybe more pointedly, what critical assumption are you currently making about your delivery frequencies, or about the amount of buffer stock you really need? What assumption are you relying on today that precise data and rigorous simulation could potentially prove completely, utterly wrong?
That time invested up front, defining the problem accurately, modeling the solutions using simulation. It's often the lowest cost investment you can make, but with potentially the highest possible return in avoided waste and improved efficiency.
Food for thought indeed. Thanks for joining us for the deep dive.
Thank you.
We'll see you next time.